Okay, good morning. Let's begin our lecture today. Today is Friday, so we will have to do a toss coin first. So let me share my screen and oops, that's not the correct button. Yep. Okay. Okay, let's flip it. Homework it is. Well, I'm glad everybody is happy. I'm happy about it too. Please don't forget to submit your homework. Okay, now the quiz is going to be changed in like modes and everything. So it's going to cost 0 points, but you can still see it. Okay, so you will be able hopefully to see all the answers. Now, I know some of you are saying you cannot see the correct answers for quizzes which I relieve. I always mark down that you can see the answers. So I can like show you in the settings, the sets you're supposed to be seeing them. So I don't know if you do not see them, why you do not see them. But you're always happy. You can always come to my office hours and I'll tell you what's going on. Now, on Wednesday, I know somebody was trying to connect to my office hours, but it didn't work out. I was away for like 15 minutes or so. My computer died in the middle. So, you know, whoever was trying to connect, sorry about that. I was like able to connect after 15 minutes or 20 minutes or so, but unfortunately, that was the way it is. So please, if you were trying to connect and it didn't work out, come today. I hope this time my computer is going to work normally. This is homework. Yes, we are doing homework this week. So today we are going to be talking about chapter 5. How did discussion go? Okay, so hopefully you know what you're doing and hopefully everything like went fine. I do want to give a couple of hints. So when you have summation notation, and I probably shouldn't be writing in chapter 5, so let me go to office hours instead. Sorry. So when you have a notation like summation of, I don't know, I squared, it's sometimes easier to see it at 1 square plus 2 square plus n square. And generally for the induction, it's easier to see it like this and see what you can substitute when it's written in that form. And again, summation says you need to take n elements and add them up. Now in question number 3, I don't know if you talked to your TAs about it or not. It used intersection in a similar way. And I want you to understand that this is again just saying A1 intersection A2 intersection AN. So you can use this one. And when you make it as +1, it's going to have one extra intersection, correct? So this is as far as, and then you can kind of think about how can I use that? Now, if you have a product, so this is product, it's going to look like that. Like, I don't know, I, then it's going to be like 1 multiply 2 multiply n, correct? So pretty much, and again, if I'm going to square it, it's going to be square over here. So it really depends, like sometimes it's visually better to see it as expanded, okay? So I would suggest trying and doing that. And another important note is if you are using something like k minus 2 to show something for k, or if you're using like, well, actually to show something for k plus 1, you need to make sure you cover 3 steps back in base case, because you're always saying not a book before me falls, but 3 books before me falls, correct? So you need to show at the beginning at least 3 books are falling, correct? So this will need to be done as each separate base case. Does it make sense? If you just use K, that's fine. But if you plan on using something like K minus 1, I just saw somebody using it, please make sure to do all the base cases you need. Because in order to say it's true for K minus 2, you need to show those base cases, okay? Okay, on that note, let's move on to chapter 5, and we are right now in section 5.3. So section 5.3 is talking about recursive definition and structural induction. So first of all, let's recall, we already heard the word recursive, correct? We heard the word recursive, but we did what? Recursion, recursive formula. What was it? Sequences, correct. This is where we talked about sequences. So let's recall that recursive formula for sequence actually has a base case, correct, of how to start, and a formula which can be written maybe like that. So we already talked about recursive formulas and how to play with them, correct, and how you can substitute things and see how the things work and how you can build the whole sequence. It's kind of connected to how we prove by induction, correct? Yes? It's a similar concept. Now we can also talk about recursive function, which we also talked a little bit about when we talked about like sequences. Recursive function. And again, sequence is also a function, correct? But it's for natural numbers. You only plug in for sequence numbers, like you have element 1, 2, 3. So it's kind of like plugging as f of 1, f of 2, f of 3, correct? So f of 1 is first element, f of 2 is second element, and so on. So recursive function is also defined using a basic step, which is specify value of function at 0, or sometimes it's 1, correct? Like depending where you want to start. And Then there is an inductive step. When you define the recursive function, it is give a rule for finding its value. Using smaller value like f of n minus 1 or f of n minus k. So pretty much you need to use smaller term or multiple. So pretty much the whole idea is, again, we already used it. We already dealt with those functions. Now we just kind of see the strong connection between inductive proof and recursive definitions of formulas or functions and so on. So they always also have two steps. One step is basic step and the other step is an inductive state. So pretty much how do you start the sequence and how find the value of an element of a sequence using some previous elements. Same for function. That's just the idea. That's just, more formal definition of it. Okay. Sorry, I know you do not see it, but I have extra windows with your comments and pictures, and it doesn't want to move. Okay, here we go. Yes. Okay, so let's do an example of a function defined in that way. F of 0 can be defined to be 5. And then I'm going to define f of n plus 1 to be negative 2 fn plus 5. This is kind of similar like the sequence I gave in the previous example. But now what we can do is we can say, okay, so can you find me f of 5? Can you find me f of 5? Yeah, so f of 1 is going to be negative 2 multiply 5 plus 5, which is going to be negative 5, correct? Yes? F2 is going to be negative 2 multiply negative 5 plus 5, which is going to be 15. F3 is going to be negative 2 multiply 15 plus 5 equal to negative 25, and you can keep on going, correct? So pretty much you can find anything you want, but as mentioned, it's going to take a while, correct? Because you're going to start from the beginning and build it one step at a time. Now, lots of times, I can give you functions which you already know using recursive formulas. So here is an example. What does it mean to have a to the power n? Well, generally, you can think about a to the power n as really a multiply n times, correct? How do you represent it recursively? How do you build? How do you structure it to give me a recursive formula to do it? Well, let's think about it. How would I create an plus 1, for example, from this formula? How would I generate it? So an plus 1 is a multiply a how many times? N plus 1, correct? So what I really need is I kind of need to say I'm taking this and multiplying it by n, correct? So now it's if this is n times, then this is n plus 1 times. Do you agree? And now I'm missing the starting position. So what is going to be my starting position? How do I start? I don't need to say how do I define the very basic a to the power 0. What is going to be a to the power 0? How do I define it? So a to the power 1 is 1. And a to the power 0 from mathematics is 1, correct? So my formula is going to look like that, right? Or like Carter said, I can represent it as a function, correct? I can say f of 0 is 1 and f of n is, well, in this case, I'll have to kind of do f of 1 equal to 1. And then a of n plus 1 is going to be a multiply f of n. And I should be consistent with my little half. Okay. Now, let's talk a little bit about common sequence Fibonacci. We already watched the movie and we already know how Fibonacci works. So now let's define Fibonacci as a recursive function. So Fibonacci. F of n is equal to f of n minus 1 plus f of n minus 2. This is in a sequencing, correct? And we need to give 2 starting points. Now, it's kind of the same as writing like that. It's literally the same idea. One is the sequential sequence, and the other is in a function way. Okay? Now, I want to show that, where do I have my alpha stated? Okay, let alpha be 1 plus square root of 5 over 2. I want to show that for n bigger 3, Fibonacci, this is going to be my Fibonacci, f of n is bigger than alpha to the power n minus 2. In other words, I want to show f of n is bigger than 1 plus square root of 5 over 2 to the power n minus 2. The question is, how can we prove something like this, okay? So what I know here is I have a Fibonacci sequence, correct? And what I know here is I have a recursive formula on how to do it, yes? And I also want to prove something for n bigger than 3. So what type of proof should I use? Induction, correct? It kind of comes very natural. You see recursive formula, generally that's what you use. The question is, how do we do it? So induction proof. In order to do induction, we need to do base case, correct? For the base case, we're going to do F0 and F1, correct? Now, in Fibonacci, what is F0? This is for Fibonacci, correct? So it's 0, correct? So let's check if it works. Is 0 bigger than 1 to the power -2? Is 0 bigger than that? No. So what's wrong? What am I doing wrong? What is not good? I have one correct answer in the chat already, but I want you to don't look and think about it for a second. What's wrong? Why isn't it working? Yes, so this is where it's always important to understand the problem really, really well. So we are missing that. We know with recursive formulas, we always start with 0 or 1 to be base case, correct? But you also need to read problem carefully. Did it ask for 0 or 1? No, it didn't, correct? It actually said n bigger than 3. So what should be my base case? N equal to 4. Okay, lovely. But in order to do n equal to 4, what do I need to know? What am I comparing? I'm saying Fibonacci number 4, correct, should be bigger. So we want to show Fibonacci at place 4 is bigger than 1 plus square root of 5 over 2 to the power 2. That's what we want to see. Okay? So in order to do it, can I just leave it like that? No. I really need to use the Fibonacci numbers, correct? So I really need to know what Fibonacci number 4, correct, is. So let's calculate. So we have 0, 1, 1, 2, 3. Fibonacci number 0, 1, 2, 3, 4, correct? Yes? So is 3 bigger than 1 plus square root of 5 over 2 squared? Well, in this case, one way is to kind of open up your calculator and check it out. The answer is going to be yes, it is working. Okay. this number is going to be smaller. So again, if you want, we can plug it in. I'm not sure I have the calculator with the square root of 5 on me, but it is true. Now, our next step is going to be inductive step. Now, this is not a type of proof I'm going to require you to know how to do. It has Yaki numbers and a couple of tricks, but it's a cool proof to see because it's a tricky proof and it has some interesting properties. Plus, Fibonacci's are extremely important. We use golden ratio all the time. I don't know if you knew it, but the golden ratio is a number Fibonacci. It's a limit Fibonacci sequence is trying to convert to, and golden ratio is a magic number. You can see it in proportions of humans. You can see it in a lot of nature, in a lot of places in nature. So now, to do inductive set, we are going to assume that for n equal to k, f of k is bigger than 1 plus square root of 5 over 2, k minus 2. Prove f of k plus 1 is bigger than 1 plus square root of 5 over 2, k minus 1. So I literally plug k plus 1 instead. So now, what do we do? What I know is I know how Fibonacci sequence works, correct? So can you tell me what is actually fk plus 1 in Fibonacci? How do you get fk plus 1? What do you need to use to get fk plus 1? You need to add two previous terms, correct? The way you do it is you add. So we're going to say, okay, fk plus fk minus 1, is it bigger than 1 plus square root of 5 over 2, k minus 1? Well, good question. I now can easily substitute that, agreed? But I'm going to have an issue. What about this disaster? Do I know anything about him? Well, the question is, do I, don't I? I have an answer of yes. What do I know about him? Well, we know it's positive. Yes, that's probably right. But I will be stuck with fk minus 1. It would be good if I can somehow connect it to this number out here. Agreed? But I only have n equal to k. Good or bad? So what am I doing now is like traditional mathematical induction, correct? Is this assumption enough for me or not? That's not good. So what type of induction proof should I use? If traditional mathematical induction is not working because I have two terms I need to look at, not just one term before me, I need to look at two. It's supposed to scream strong induction at you. So what we need to do, what we should do, is we should say, yay, we're going to do induction, still inductive step, but we are going to assume that for all n less than or equal k, we get that. And yes, it's correct. I can always use strong induction because strong induction is also always going to give me K before, correct? So strong induction, the name strong has a meaning, correct? It's stronger than mathematical induction, and actually it includes mathematical induction in it. So yes, you can always use that. But traditionally, mathematical induction is more common, and most of the times you only need one down, so people do not really write it. But yes, like this is already includes n equal to k, correct? So it's already there. This one is stronger. This one is better. So now you can see how it's going to make our life better. So now I'm going to leave it as a big question mark. And I can kind of tell you that, okay, we have both of those. And for both of them, condition stands, correct? So I can use my induction step. So we know by inductive assumption that f of k is bigger than 1 plus square root of 5 over 2k minus 2. And we also know that fk minus 1 is bigger than 1 plus square root of 5 over 2 of k minus 3. Agreed? So now, if I'm going to replace fk and fk plus 1 with each of those, am I going to make the whole thing smaller or larger? So if I replace fk with that and fk minus 1 with that, will this sum of those two numbers be smaller or larger? So if I call A fk plus 1, and B is going to be 1 plus square root of 5 over 2k minus 1 plus 1 plus square root of 5 over 2k minus 3. Please tell me who is larger, A or B? Okay. A is larger. Agreed? Now, if I can show B is bigger than 1 plus square root of 2k minus 1. Is it going to be good enough? Is it also going to show that it's smaller than A? Well, let's see. We know A is larger than B. And if we can show B is really larger than this number, then it is going to work. Now, it is really important to understand it because if it would have been other way around and A would be less than B, it wouldn't work. So you only can make your thing smaller and smaller and smaller. You cannot make anything larger. Okay, that's important. This is like always a case of inequalities. So let's work. Let's do some math. We know this is bigger than B using induction assumption. What power is smaller, k minus 2 or k minus 3? K minus 3. So can I factor 1 to the power like that? Can I factor it? If I'll take k minus 3 things from here, how many are going to be left? Just 1, correct? And how many things are going to be left in here? None, correct? So this is good. This is what we have. Now let's do it. Let's just plus square root of 5 to k minus 3 multiply 3 plus square root of 5 over 2. I just did math, common denominator, and I added it up together. Okay, that doesn't really look what I want. I kind of somehow want to connect it to, where is that? K minus 1, correct? I'm going to show you the cool, interesting observation. Alpha square, yes, is 1 plus square root of 5 over 2 square, correct? Let's compute it. So we have 4 here, and we are going to have 1 plus 2 square root of 5 plus 5. Agreed? I opened up parentheses. And now it's going to be 6 plus 2 square root of 5 over 4. Now, both 6 and 2 are divisible by 2. So we have 3. Oops. We have 2 multiply 3 plus square root of 5 over 4. But guess what? That looks awfully familiar. I strongly believe it's very cool. But they're identical, right? So pretty much I can replace it. Which is exactly what I want. So my induction, oops, I don't know why I wrote 3 here. My inductive proof is done. Okay. So your homework from this section, you will need to prove some sequences using recursions. It's not, nothing is going to be as complicated as what I just did. This was just kind of, cool because it's Fibonacci and Fibonacci is cool. But you will have some, you will go with like recursive functions, recursive definitions, and a couple of proofs in this homework. So this is your homework assignment, and it is from section 5.3, which is going to conclude chapter 5 for us. And we are going to go into a totally new chapter, which is going to bring some new topic for us, something we didn't do before. So we are going to be talking about counting. Do you all know how to count? Do you know how to count? Well, we'll check. So section 6.1 counting. Oops. Okay, so example. I have 18 math majors and 45 CS majors in a class. In how many ways can I pick math and CS representative? Well, actually, it's not a big class. Our class has 120 students, and this class only has what, 50, 60 something. It's a pretty small one. No double majors. So in how many ways can I pick one? I need a representative from math and a representative from CS. How many different combinations do I have here? Yes, a lot is a good answer, but unfortunately not really the correct one. Yes, Cody has the correct one. He is saying there are 18 multiply 45 ways to do it, and I have to agree. I will have that many options. So that brings us to a rule. Which is going to explain to us why it is 18 multiply 45. So suppose a procedure can be broken down into sequence of 2 tasks. If those tasks can be done in N1 and N2 ways. So task 1 can be done in N1 ways, and task 2 can be done in N2 ways. Then there are N1 multiplying 2 ways to do original task. So pretty much, let's think about it. I need a representative from math. How many people I have in math? 18. So how many options for me to pick up one representative for math? 18, correct? Makes perfect sense. Good. I have 45 computer science majors. It is, after all, a computer science class, right? So let's grab one computer science major and how many ways I can do it. And 45. Now the question is, why do we really multiply them? So assume I picked my math major. Here he is standing in front of me. I can still do the combination of this one major with 45 of my CS students, correct? So there are 45 options for him. But this is only one version of picking up the one math person from 18. The second person from math I pick also will have 45 options for the CS, for the second person he's going to be working with. So it's product rule. So you multiply them together. Now, let's go and use this rule again. How many functions f from n to n can we have? So I have m elements in domain, n elements in thing. Yes, people are going to think m n, correct? Or not? It is still product rule, but you have to think about it. So what I'm doing, I have 2 dots here, and I have 3 dots here. How many options my first dot has? 3, correct? How many options my second dot has? Also 3, correct? Now, if I'm going to add one more out here, it is going to be another 3. It is product. We are dividing it into tasks. We are putting every element from range, no, from domain, and we are trying to map it to the main. And then each task we can do in n ways. So actually, correct answer is n multiply n how many times? M times. So actually it's n to the power m. Still product. Now what if I want one-to-one function? And I will know that m is less than n for sure. How would I do that? Well, let's try and separate it again. The very first dot, in how many ways can I map it? This first dot, how many options it has? In the top thing, I have one dot. In how many options will she have? 3. Now you mapped it. So assume I picked this one. Yes? Assume I picked one. In how many options can I map to? Aha, I only have 2 left. What about the very last one? Just 1 left. Aha. So what happens here? At every step, I illuminate 1 dot, correct? So it's going to be n multiply n minus 1 multiply n minus 2. Where am I going to stop? Well, since I never told you that they're going to be the same, it's going to be n minus m plus 1. So it's not exactly n factorial. Now, if m equals n, then n factorial is correct answer. Okay, let's keep on going. The sum rule. If tasks can be done either in one of n one ways, or in one of n two ways, then it can be done in n1 plus n2 ways. An example is back to my classroom, 18 math, 45 CS. Now I just need one class representative who is going to be in charge of everybody. He's going to communicate my message. In how many ways can I do it? So I need to sum all of my students and pick one, correct? So it's going to be 18 plus 45. Okay, on that note, we are done for today. Have a good weekend and don't forget to submit the homework.